Okay, good afternoon, everyone, and thanks, Ben, for the introduction. My name is Arnaud Folk. I'm from CSIC, and we will also have today here Piero Lanucara from Cineca. And we also want to thank a lot of people from ChEESE that helped us to prepare this presentation, and in particular, Vadim Montelier from CNRS, Jose Garcia from HLRS, Brian Wiley from Jülich, and Marta Garcia from BSc, and some other people from the ChEESE Work Package too. So we have prepared the presentation like in two blocks. I will give the first block, which essentially is a quick introduction to the ChEESE Center of Excellence, and then Piero will take over and present you which is the strategy that we have in one particular work package 2 of ChEESE for preparing the codes. And then he will also show a success story, showcase of the SpecFEM 3D code. So let me start by introducing the ChEESE Center of Excellence. ChEESE essentially is the Center of Excellence in geophysics, or if you want, on geohazards. And actually, we are on the second phase of ChEESE. The first one, we just started some years ago, started by considering a series of phenomena. In particular, we had 4 domains. We had earthquakes, volcanoes, tsunamis, and magnetohydrodynamics. And during this second phase, we just started last year, we are enlarging the number of domains that we have by adding also geodynamics and glaciers. So actually, we have right now 6 different domains of geophysics that we tackle within ChEESE. No? And one of the things I think, in my opinion, that makes ChEESE particular is that we cover the different views of exascale, capability computing, capacity computing, and urgent computing. Capability computing is what most of the people understand by exascale. So essentially, it's solve problems that we couldn't solve so far because we didn't have the large enough machines, let's say. No? So it's single, monolithic, very large scale executions. But we also have a lot of interesting cases in which that we call capacity computing, where we have ensembles of problems made of many scenarios, each of which can actually be solved with a smaller scale machines, petascale range, or even less. But then we solve for different problems, like, for example, data inversion or model data simulation, uncertainty quantification, etc. We need to solve simultaneously hundreds or even thousands or tens of thousands of these single scenarios. So that actually we can reach exascale not through a single execution, but through a workflow that articulates and orchestrates the execution of all these scenarios. And then we have a third pillar, which is urgent computing, in which we can solve either a capability computing problem or a capacity computing problem, but under very strict time constraints. So we have to make time to solution as smaller as possible because we are dealing with emergency situations. ChEESE itself also sustains on 3 pillars, which are codes, what we call pilot demonstrators, and what we call simulation cases. In the second phase of ChEESE, we have 11 flagship codes on the 6 domains that I was mentioning before. Then we have 9 pilot demonstrators. Pilot demonstrators essentially are workflow that address some capacity, or urgent computing computational challenge. And then the simulation cases are the simulations in which pilot demonstrators actually materialize. And we use the simulation cases to enable services on aspects that are relevant from a social point of view, considering, for example, early warning systems, hazard assessments, or the use of urgent computing. This is the list of the 11 flagship codes that we have in ChEESE 2. As you can see, it's quite a large number of codes. We have 4 codes on computational seismology, 1 on magnetohydrodynamics, 1 on modeling tsunamis, 2 on modeling different aspects of volcanology, 2 more on geodynamics, and finally 1 more on glacial modeling. As you may see, some of these codes are accelerated. This is because the codes that are accelerated were inherited from ChEESE 1, and we did during ChEESE 1 a very strong effort on porting the codes. And for the rest of the codes, of course, there is an ongoing activity for porting all these codes to accelerators. Many of these codes, in particular 7 of these codes, also have mini apps, and we use mini apps for co-designing. We have a specific work package dedicated to co-design with HPC vendors, and in particular with the EU pilot and the EU PEX initiatives or projects. All the codes are open source and are used on one or more of the pilot demonstrators. I also put this slide to make evident and to show the wide range of typologies of code that we have, because when don't think about geophysics like something homogeneous. Actually, we address a lot of different problems. Some of the codes or let's say, are concerned with wave propagations. Other codes are more could be defined as multiphysics CFD. Others, a particular case of CSD that is geodynamics. Others address shallow waters or kind of variation of shallow water equations. And finally, we also have a code that is a advection diffusion sedimentation code, so essentially modeling transport equations. As you may see, this is quite diverse and gives an interesting ecosystem for testing, no? Also because the algorithms behind these codes is also very diverse. We have finite elements codes, we have finite differences, we have finite volumes, we have spectral elements. So we also have a quite diverse typology of solving algorithms for all these problems. And this makes ChEESE quite let's say, unique and particular CoE, no? In ChEESE 2, we have 7 work packages, but I want you to focus now on work package 2, 3, and 5, because are the ones that are more, let's say, related to the codes, no? In terms of the preparation activities, work package 5 is centered on improving the physics of the model. So that's adding new functionalities, new parameterizations, different types of couplings, forcing terms, etc. So this is more related to the physics of the code. Then we have work package 3, which is on co-designing with European HPC vendors and technologies, in which we use the mini apps of these codes for testing new and emerging architectures. And then work package 2, which will be the focus of the talk today, which is probably the thickest one in terms of code preparation activities, in which we are doing a range of activities that you can see listed in the table. But in particular, today we will focus on task 2.1, which is the auditing of the code and the role that the related POP metrics is performing. In terms of pilots, as I said before, we have 9 pilot demonstrations. You have here the list here with the initial technology readiness level that we had at the beginning of the project and the target value that we expect to achieve by the end of the project, no? As you can see, the pilot demonstrations are real applications of the codes on real scenarios. Most of them are located in Europe, but we also have some other scenarios beyond Europe, like, for example, in Greenland, or in other places like simulation of the Tonga case that we had in 2022, or the global tsunami hazard map. All these pilots, in fact, they materialize in what we call simulation cases and will produce open data sets that we will share at the end of the project, enabling of services based on urgent computing. And then they will also fit different thematic core service of EPOS. EPOS stands for the European Plate Observing System, and it's a kind of pan-European infrastructure for data and services that is quite relevant to our community. This is just the list, just to give you an idea about the list of these 15 simulation cases, which, as you can see here, also contain both capability, capacity, and urgent computing cases, no? And in particular, 4 of these 15 are what we consider scientific grand challenges, which are really very large capability use cases in which we will need to make use of full machine executions to meet our goals, no? This is the 4 that you can see on the one but last column. And then the expected outcomes, as I was saying, they will be mostly open data sets, but we also will have enabling of urgent computing services and thematic core services in EPOS. So we have actually 3 typologies of services. One is the urgent computing services. We have 4 pilots that will materialize on enabling of services, and we are doing that in collaboration with what we call the IUB, industry and user board members. So these are stakeholders that are monitoring and ChEESE, and are helping us to design or co-design these services by means of what we call trials, which are long-term exercises in which they impose the requirements, and we try to meet the requirements in terms of model resolution, time to solution, area covered that needs to be covered, etc. for these services. No. Then we have two more services that will directly go into thematic core services in EPOS, in particular thematic core services for tsunamis and volcanoes. Here we will produce the first European scale tephra hazard map, that's for the dispersion of volcanic products in the atmosphere. And then we will also produce a global tsunami hazard map. So that's a global scale hazard mapping for tsunami inundations all around the world. And then there is a third service in which all of these 11 codes will be deployed on the EuroHPC systems following a CI/CD approach. This, as you know, is done in collaboration with Castiel, not only for ChEESE, but also for the other CoEs. Probably the different thing in ChEESE is that we are doing that by setting up an ecosystem for an automatic quality code quality assessment as a service, so that all our codes need to have a certification, need to have a badge, a golden badge, a silver badge, or a bronze badge before going into this CI/CD in the EuroHPC systems. In terms of ChEESE and POP, which is the focus of the talk today, I have to say that it's, let's say, a sustained collaboration in time and very, very fruitful. It started back in ChEESE 1 at the time with POP2, in which we already performed 2 audit campaigns for the 10 codes that we had at that time under the umbrella of ChEESE 1. No? So that's meaning we audited the codes 2 times, one at the beginning of ChEESE 1, and then another audit campaign at the end. Though that supposed a total of 20 audits for the ChEESE codes. Now, under ChEESE 2 and POP3, we are doing essentially the same. So we already did a first audit campaign last year, and we will do, before the end of the project, a second audit round to audit the 11 codes. So if you make the numbers in total, we will, the idea is to have 4 campaigns for all these codes. It means that we will do at the end more than 40 audits. This is quite a substantial amount of work. In terms of the purpose of the audit, in ChEESE 1, actually we did the audits only to identify code bottlenecks. So it means that we audited the code at the beginning, and then all the optimizations that we did on the codes, or most of the optimizations, were audit-driven. It means that the audit served to identify flows, bottlenecks in the code, and based on the results of the audit, we performed the optimizations. We are doing a similar thing in ChEESE 2, but actually we have expanded the role that POP plays, because in addition to identify code bottlenecks and drive the optimization of the codes, we use also the POP metrics to define a baseline for the code performance. And then we use the POP metrics actually as KPIs for monitoring the evolution of the codes, of the code performance, performance through the project, no? And we are doing this, or we will do this using TALP in particular. In terms of audit tools, in ChEESE 1, we use both Scorpy and Extrae. We use Scorpy for what we call at that time level 1 codes, which were the codes that when we started ChEESE 1 were more prepared or more evolved. And then for level 2 and level 3 codes, we use Extrae. Now we are using a kind of more diverse range of auditing tools. This is quite system dependent, but in addition to Scorpy and Extrae, we are using also other audit tools. In terms of the audit focus on ChEESE 1 was mostly on CPU. And this is because at the beginning of ChEESE 2, very few codes were ported. So porting was the main effort during ChEESE 1. So the audits were mostly focused on CPU. And on top of that, the hybrid metrics POP metrics for hybrid architectures were not fully available, or were still under development at the time. Now, this has changed now in ChEESE 2, and we are auditing both for CPUs and GPUs using hybrid metrics. And then another thing which is new with respect to ChEESE 1 in ChEESE 2 is that some of the codes are already applying for POP second level services for correctness check, energy efficient studies, or advisory studies. So we have, let's say, enlarged the collaboration with POP even more during ChEESE 2. So in ChEESE 2, as I said before, we already did last year a first audit campaign in which 10 codes were analyzed. You have here the list, the programming model of the different codes, the code version, and the systems where we did the audit. So essentially, we did on Leonardo, on Lumi C and Lumi G, and on Vega, and the different audit tools that we use it. So it's Scorpy, Xtry, but also Scalaska and MPIP, DLB Talp, etc. So you have here the list. I have to say that it went very well, as in ChEESE 1, but nonetheless, we encountered some issues, not because of POP, but in general because of the ecosystem that we have, no? And one is the heterogeneity of the performance analysis tools across Europe. So there is no a unique, let's say, or not an ecosystem of tools which can be homogeneous across the different EuroHPC systems, and this may be a problem for us sometimes. And also another issue that I think that the CoEs have is that if you want to do an audit, normally, unless you have in-kind resources, because you belong to a supercomputing system, you will need to apply for some kind of project access, name it a benchmark or development access mode. And this is okay, but the problem is that if we have to do this 40 times, it's quite an overload, no? It's quite, let's say, demanding in terms of preparing projects and so on. So we don't have right now for the CoEs a mechanism in place, like, for example, an audit access mode or something like that to perform all these activities. And this was kind of, as I said, overloading, no? And I leave it here. So I give now the floor to Piero, and he will explain, he will enter more into technical details, explaining the Work Package 2 strategy, and then showcase the example of Spectrum.
So, okay, thank you very much. So this is the part of the story when we describe the work done, of course, in the framework of ChEESE 1 project, and that is ongoing in the framework of ChEESE 2P project. So in particular, the Work Package 2. So Arnau already presented the work done in the framework of the ChEESE 1 project, but in particular, we are now focusing on the activity of the Work Package 2 in the current ChEESE 2P. So we have 11 flagship codes. We have a lot of pre-exascale and future exascale systems, particularly Lumi, Leonardo, Nostrum 5, with different flavors in terms of CPU, GPU, networks, and so on. So we have a lot of aggregated computing power, of course, that you can use, but with a variety of different accelerated architecture. So basically, this is the same of the ChEESE 1 project, but we are now struggling with this in the ChEESE 2P now. So this is the Work Package 2 activity. So basically try to optimize, tune for the 11 flagship codes on current pre-exascale architecture. And this is the methodology, which is basically for some part very, very similar to the methodology we had in the ChEESE 1 CoE, but with some relevant difference. So in particular, this is the part which is more or less the same of the ChEESE 1. So we start to the first code audit, then we have an improving of the performance after the first code audit, a second audit, and then a final step of improving, porting, and report. So basically, this is the same. We use the metrics from POP, exactly like in the ChEESE 1 project, but there is one task, additional task, which is the task T2.4, which is related to the monitoring of the performance of exascale in particular. So trying to overcome some limitation that we may expect from the previous Work Package 2 methodology. But this is very similar in some sense. Okay. So concerning the audit, are now already described the process, which is in some sense very similar to the audit process in ChEESE. So the goal is exactly the same. So set a performance baseline for optimization work and progress monitoring, and also, of course, identify performance bottlenecks. So the idea is to, exactly like ChEESE, perform 2 performance audit campaigns in different steps and measure the performance of the flagship codes via using the so-called POP metrics. So this is the statistics from the deliverable D2.1, which was finalized by HRS. Thanks to yourself for providing. And of course, this is the outcome. So in particular, as we already mentioned, we targeted EuroHPC systems like Leonardo, Lumi. Of course, at the moment, my Nostrum Pi was not in place, but this is the situation. So what we can say is that, of course, a lot of useful information, scaling campaign, which strong scaling, of course, maybe some limitation in terms of number of MPI ranks or GPUs that you can use in the audit, but we will go to this point later. As I now already mentioned, some challenges the access to EuroHPC systems, which is challenging and complicated in some sense. You need to cope with this. And also, maybe another additional point is the availability of performance analysis tools on EuroHPC systems, and in particular, having these tools up and running and with all the features that those complicated flagship codes needs. So this is another point of interest, of course. Okay, so we try to also having some highlight, of course, in one slide. The deliverable is very huge and it's impossible to have this situation, but basically we want to highlight to measure facts, no, in the analysis. The first point is related to an execution of LAMM up to 64 ranks, CPU investigation on LumiC. So the idea is having some snapshot of the execution on some bottleneck in the performance and where it's located. So this is very important highlight from the audit campaign ChEESE, of course, thanks to the POP investigation. And in this case, you can see, for example, in green, there are dominant MPI operations, particular MPI weight all in green, collective in purple, and you can see there is a lot of these issues. So performance analysis is very relevant to achieve an investigation of the performance bottleneck, and so this is very useful. Another important point you can see the picture in the bottom is having a quantitative measure of the performance obtained in a scaling campaign. And this is relevant, of course, because this is one of the main achievement of the task, main achievement in ChEESE, so improving the scalability of the application, in particular CPU and GPU execution on EuroHPC hardware. So you can see in this case, of course, you have a representation of the POP metrics, in this case for the GPU execution. And you may see there is some issue, but this issue is mainly related to the fact that you have, basically low contribution from the CPU side, while the metrics are considering all the resources, of course. So globally, the situation is very good. This is for IC on Leonardo execution, and the loss of performance is mainly related to the CPU side. So in the end, it's very useful to have this kind of investigation in POP, in ChEESE. So we are very happy with this, and this work will continue in the next steps. But as we already mentioned, work packet 2 is not only to measure the performance of your application or EuroHPC hardware, but it's more now in ChEESE 2. And this is part of the new task in ChEESE 2P that is related to increasing not the performance, but the performance portability of flagship codes for different accelerators. Because in a previous slide, you already see that you have not a monolithic situation in terms of accelerator system. You have a huge variety of accelerator systems like Leonardo, NVIDIA GPUs, Lumi, AMD GPUs, probably in the future something else, different devices, different performance. And so this is something to take into account. So this is part of the task of TIGO2, and this is an important story in the ChEESE 2 project now. And basically, we want to describe a little bit the methodology of this task. So the first part is, of course, the dissemination. The huge variabilities, not only in terms of hardware, of course, you need to cope with huge variability in terms of programming languages. So Fortran applications, C applications, C++, but also in terms of parallel programming paradigm. So for example, you may exploit intrinsic parallelism in Fortran, OpenCL, SQL, for GPU programming, CoCos as a performance portability layer. So the idea, which is part of the task, is to increase the knowledge of the team, internal teams, and the code owners in the work packet 2 in order to work with. So a lot of webinar taking place, and other will be in a next future. Another important aspect of this task is the porting strategy. So we need to start from an application, trying to investigate the different way in which you can solve basically the same problem, but using different programming language strategies or using a different tool. So this is part of the porting activity. This is done basically at the terms of mini apps that are now already described in the previous presentation. And so this is here a huge intervention of the mini apps so mini apps are used to evaluate and to write different version of the mini app, but using different hardware level. So this is the porting campaign. And then, of course, this is the crucial step. So increasing the performance flagship codes, measuring the performance portability of the available mini app or flagship codes on different available hardware. So this is done using metrics, particular metrics that are available from the literature. So the performance, and you can see here a reference. And of course, this needs to be organized in a campaign. And you can see in the bottom typical output. So in this case, you don't have only performance measurement, but you have a performance portability plot in which you have different device, different version, different programming model, and you measure the efficiency and the performance portability efficiency of this particular set of mini apps or flagship codes in the EuroHPC arena. Of course, for this kind of investigation, you may only have hardware which is still not available in the EuroHPC, but for example, some software development vehicles that can be from vendor. So the investigation is more, of course, at a wide range in some sense. So this is the task TO2. So this is new in ChEESE 2P, and we are really, really curious also to see the outcome that will be produced now in the deliverable TO2, which will be available within the end of this year. So another important story, of course, is the optimization for exascale. So this is the other part of our pie. Of course, this is more related to instead taking the observation and recommendation available from the code audit or other improvements from code owners, put together and try to optimize the performance of the flagship code, of course, taking into account that you may have single heterogeneous node performance issue, multi-node performance, for example, at MPI level, algorithmic improvement, I/O, and so on. So this is really the part which is more related to the exascale features, and of course, this is the flagship codes in their availability is taken into account for this investigation. So not mini app in some sense, but the real application which can be used also for production purposes. So this is the part, but as we already mentioned, this is now another story which is the related to the continuous performance efficiency monitoring. So the idea is that to try to overcome maybe some limitation that the current use tools may have in sense of their to be more light, of course, and measuring the parallel flagship codes at runtime, in some sense. So we want to have a tool that is able to measure our performance without coping with the large traces, for example, that you may have in a really production application running at a large number of cores or GPUs. So this is a story which is really important in ChEESE CoE, Work Packet 2. This is part of the Work Packet 2 investigation. In particular, TALP is the tool they use for this story. And so the idea in the Work Packet 2 is basically to develop new features in TALP, because we already mentioned that an important part of the story is now having GPU execution, GPU support, multiple languages, multiple features, and so on. But also, of course, use TALP in conjunction with the execution of larger parallel solution and obtain, of course, the POP metrics, in some sense, more easy than the way we use for adding POP metrics with the SCORP, Scalaska, Extra, and so on. So this is another important part of the story of the Work Packet 2. And okay, this is really from a theoretical point of view, but we want to address now, of course, maybe a more useful for you and interesting also part which is related to a particular showcase, in particular SpecFan 3D. SpecFan 3D, which is one of the, of course, most used in the community of seismology. It was also in the ChEESE project. There is a huge activity for SpecFan 3D also in ChEESE, but also in other projects. So it's important to highlight the activity, which is based on top of SpecFan 3D, also from the production point of view. So this is the method, in particular spectra element method, so very suitable to parallelization, CPU, and GPU implementation based on top of MPI for domain decomposition. You may have different flavors, so seismic wave propagation, full 3D models, elastic, viscoelastic, fluid solid interaction, and so on. So you have a different physics, and in particular in the framework of ChEESE and the task T2.1, very deep investigation was realized using Leonardo and a suitable test case. In particular, weak scaling campaign was done and strong scaling campaign up to 512 GPUs. It's worth mentioning to say that SpecFan3D has been already optimized for different GPU architecture using CUDA and IP according to different GPU programming model, different architecture. So this is SpecFan3D, and this is part of the analysis that was done in the framework of Work Packet 2 task T2.1. So thanks for copies of Brian Wiley. You can see a reference, and you can see in particular that you have basically no issue from the point of view of performance for weak scaling, while you can see a picture on the right, there is some issue in terms of strong scaling, particularly 512 GPUs. So the analysis demonstrated that there is a good balance, of course, between, so yeah, no problem of GPU load balancing, but this metric is related to the orchestration efficiency that includes MPI communication, kernel flow, cellular device, I/O, and so on. Basically, performs poorly in this configuration up to 512 GPUs. So at some point, MPI point-to-point communication time has to be fully overlapped by GPU compute kernel. So this is an highlight, of course, for the performance, not only for this benchmark, of course, but also for possible production run in which you may use a large number of GPU or CPU or something like that. So this is very important outcome, and of course, it will be probably fixed in the result will be available in the deliverable D2.2. Another important highlight from SpecFan3D is related instead to the performance of the different kernels. For example, this is the execution, which is built on top of CUDA, of course, so suitable for NVIDIA GPU devices. So those are two highlights in particular. You can see in the picture, in the above picture, that there is some problem with kernels are well balanced, but there is some problem with kernel execution much faster, the interior compared to edges. And instead, in the picture of the left, you may see there is a problem with another GPU accelerated routine having a very long synchronization time. So this is account for most of the CUDA synchronization time, over 30% of total CPU time. So those are highlights for ChEESE, of course, but also for code owners. So you should now be able to put your hand on your application and improve the performance. So you can improve performance from the communication point of view, but also in the kernel related to the parallel execution. So this is very important from our side, of course. But why we need to cope with this? Because, as I've now already mentioned, we need to use this tool for not for benchmarking only, but for solving scientific challenge. So in particular, SpecFan3D is used by a team from CNRS, so Vadim, in particular, collaborators, for this problem. So numerical assess the underwater noise pollution and seismic risk induced by unexploded ordnance disposal in the by ERS in France. So the problem is there's this disposal of unexploded ordnance generate, of course, intense underwater noise that can disrupt marine life. So it's very important from this point of view. And of course, this is near a populated coastal area. You can see in the picture, and can generate seismic wave, pose risk to the coastal infrastructure. So you may have damage or something like that. So why use SpecFan3D for this, because we already mentioned this is a 3D full waveform modeling that allows accurate simulation. You have complex interaction between acoustic waves in water and seismic waves in the seabed. So you are able to model these kind of problems. So this is the challenge. A preliminary investigation up to 30 Hz, because this is an important parameter for the simulation, was done using 1,000 GPUs in the petascale machine Marconi 100, but of course the idea is to increase the precision of the simulation and have the simulation more precise and more powerful, of course. So this is the issue. This is an outcome of what we want to measure. You can see from the picture. So this video shows the vertical particle velocity on the sea bottom, and in particular the shaking of the surface while seismic wave propagate. So this is the execution that was done on Marconi 100 in ChEESE, and of course this is important to estimate, in some sense, the maximum shaking we can expect, in particular for anticipate some damage in the building that are surrounding the coast. So what about the future? So the idea is to use SpecFan3D, so passing from 30 to 100 Hz, of course. So you have a reduction in the element size. So in particular, very huge number of elements. So 1 billion of elements and 4 million of time step, with an increase both in the memory required for the simulation and the runtime modeling, of course. So the idea for this very, very challenging simulation is to use the improved performance portable version of SpecFan3D from ChEESE CoE, but of course also to use, you need really exascale computing, so LUMI, Leonardo, Nostrum 5. So the size of the resources you need is very, very high. So this result, very large meshes, pushing current supercomputer to their limit. So this is the idea, and this is why we need very improved performance version of this flagship course for the investigation. So try to summarize, as are now already mentioned. There is, of course, a very established and productive cooperation between ChEESE and POP, and ChEESE 1 and ChEESE 2. We have a lot of codes, so we present the result of SpecFan3D, but of course we have 11 codes in ChEESE CoE. We had 10 codes in ChEESE 1. The idea is to audit the flagship code to identify code bottlenecks, establish code performance baseline via POP metrics, and also in ChEESE CoE continuous monitoring based on POP metrics via TALP development and use. And additionally, as I've now already mentioned, some ChEESE codes started making use of POP services. Some additional takeaway from our side. We are managing really complex applications that are now ported from CPU to GPUs in different flavors. So in our idea, POP tools need to continue to improve their functionalities and evolve. Because the codes are evolving, tools need to evolve at the same time. And another important point is that we need really metrics, of course. So performance metrics are very useful. We need to enlarge the performance metrics to different devices, so in particular GPUs, but also we mentioned performance portability metrics, and so metrics are really the key of success of this investigation. So that's all from my side, and I think I can stop sharing.
Yeah, thank you very much, Arnaud and Piero, for this very interesting talk. And I understand it's hard to summarize all this work which went into the past years in this very nice collaboration. So the floor is open for questions. So either you can type them in the chat, or you can just also raise your hand and unmute if you want to ask the question directly. So while people are thinking and typing, you mentioned that you looked also this time into like using our second level services. Can you provide some details? Was it more on the energy efficiency side, or was it on what other services did you use beyond the performance assessments?
Can you? I know that at least 2 codes in ChEESE started to do that. I mean, we're initiating this collaboration now. For example, there is one code for today in particular that apply for energy efficiency and for correctness check. But I guess that among the different things that you have in your portfolio, all of them are of interest to some point, to some or another for the different codes. So we are also encouraging the codes because some of the people were not aware about this service that you offer. So the first thing that we did is kind of explaining the code owners the different options that they have to apply for it, and some of them are starting to apply. But this is something quite recent, let's say.
Yeah. And it was interesting to hear that, like, kind of like the issues which still prevent us from doing these services very efficiently. So would you say for this specific campaign, I mean, it was a huge campaign with 11 codes, was the biggest one getting access to the systems, or the availability of the tools on these systems, or was it both bad?
You want to take it? Well, I can say my part. I mean, access to the system was not an issue, was an extra work, no? Because all the codes managed to get a benchmark of development. It's not a problem in the sense that that is something impossible to get. You get the hours, but it requires some
Okay, it's just work. Okay.
Just work, yeah. And then limitations also for regarding the resources that you have in a benchmark or in a development access mode. That sometimes you maybe want to do a full scale audit and you cannot, simply because you cannot apply for a large number of resources for the audit. So there are limitations also. Then on the other part, maybe Piero will answer better than me, but it was not easy to find the audit tool that you wanted in the system that you wanted. And so all this combination of auditing systems, auditing tools and systems is probably not a full matrix. Sometimes there was an extra effort of installing with the help of the POP teams, installing the audit tools, testing. So it was quite extra work, I would say. No, Piero, maybe you can.
Yeah. Okay.
Yeah. No. The support from POP is excellent. The problem is that we have 11 codes, different flavors, so it's not easy to accomplish. But yeah, the support is really excellent. Of course, this is complex. Having this situation, in particular for ChEESE, we have 11 flagship codes.
Okay.
Yeah.
Yeah, I mean, we have the same issue with you. We have all these different systems with all the different architectures, operating systems, how they are organized and running. For every one of our tools, and we have like at least like 2 sets, but like if you take also Macau and the energy efficiency, it's like even more. We have the same issue, like getting accounts on all these systems, working with the local teams to get all the tools installed. And one of our KPIs is that all our tools are installed on all the EuroHPC systems, but I I guess it will take us a while. I hope by the end of our project. So for the second round for the second services, hopefully this is better. Okay.
Maybe one question here from Christoph.
Sure.
For other CoEs, if they want to approach POP in a similar way, maybe one question to Piero and the ChEESE project is, what do you think is necessary to prepare such a campaign? And maybe then also to Bernd the question, what would be helpful from another CoE that the audits are done quickly and processed efficiently?
Yeah, of course, this the way in which we use the POP tools now is well shaped now into the work packet 2 methodology. As we have two different campaign, one at the beginning of the project, one after. So I'm not aware. This is for example, this is reasonable. So maybe, yeah, from the point of view of the interaction with POP, I mean, the work packet 2 methodology looks very efficient, in particular. So this is also useful for other CoEs. In particular, if you have the situation in which you have different codes running on different systems using different programming languages and ported to GPU using different GPU flavors. So if you have really an heterogeneous situation, I mean, the methodology from ChEESE work packet 2 may have, of course. So this should be as a baseline for performance improvement. Of course, your mileage may vary. If in this CoE you have only one application port, maybe this is not needed.
Yeah. I think it's clear the more codes are involved, the more systems and more teams, the more complicated it gets. But I guess Jose can provide, because he was kind of managing the campaign from POP side, he can also say more concrete words than me for this.
Yeah, so exactly. So I was managing this assessment campaign from the ChEESE side, actually. And in hindsight, the biggest challenge was that we tried to do all 11 codes more or less in a synchronized fashion. So assess all codes in the same small range of time, which was like 3 months. And that was, in hindsight, the biggest organizational challenge. So next time we do this, I would say we don't try to have all the codes ready at the same time and analyze at the same time. Then it's much easier, I think, to organize this for all parties. Also for the POP side, they had to do a lot of analysis in a short time. So having more asynchronous mode of operation would be, I think, next time I would try that. I don't know whether it's going to be better, but I think it's worth trying that.
Okay.
I also agree that this narrow time frame was kind of challenging, no? And we foresee the same. Maybe we can relax it a little bit for the same audit. Then there is risk also that you plan something, and maybe for the timing of your project, you have to do it between 2 particular months, and it happens that there is a stop for maintenance of one particular system. So things that are like this that are difficult to foresee in advance. So it is better to have a buffer of security, let's say, and relax a little bit more. So I fully agree. Yes.
Okay. Yeah, I don't see any further questions. So thank you very much, Arnaud and Piero. I think with Jose, you will be in close contact, and we look forward to hear more about details, what kind of specific things you want to miss in our tools so we can improve them for the second round. Our tool developers are eager to hear about that. So yeah, thanks again for doing all this work. Thanks again for your time to present that here to this group in our webinar. So thanks everyone. This is basically the end of this webinar, and have a nice day, everyone. Bye-bye.
Thank you. Bye-bye. Thank you very much.
Bye.